Hi guys, it's me. I'm sorry I'm home again, absent, so I'm going to try to quickly do the notes to finish up enzymes. Again, I'm going to go fast just so the recording is short, but you can pause at any time. So you're starting here in your enzyme notes, where we ended up last time, and we talked about how enzymes bond with substrates, they lower the activation energy to help them react, and then they spit out the products. And they speed up the chemical reaction by doing that. And we talked about how they can do it with different kinds of reactions. They can either do it when we're to build reactions, anabolic, or to, my pen's not working, to break down. All right, we can do it to like build molecules like that. That's an anabolic reaction, or take a molecule and break it down like that. So enzymes run all kinds of reactions. Okay, so what is happening in the enzyme substrate complex? Okay, when the substrate is in there in the active site, it's lowering the activation energy. Okay, which we sometimes abbreviate as E with a little a. Okay, so what is the activation energy? Okay, the activation energy is the energy required to destabilize some of the chemical bonds in the substrate in the catalyzed reaction. Okay, in other words, it's the energy required to get the reaction started. Okay, I think that's a better definition. The activation energy is the energy required to get the reaction started. Okay. Oh, I think that's what we were supposed to write right there. Okay, sorry, I'm not. Just write that right there or anywhere, it doesn't matter. So note that the enzymes, they lower the activation energy required for the reaction to occur, but they do not change the energy, which we refer to as G, the free energy, of the reactants or the products. And so, without getting too much into the chemistry, it's telling you to draw a graph below. But molecules have certain amounts of energy. And so, let me see if I can switch to my PowerPoint here. The enzyme's not changing if it's in like an uphill or a downhill reaction. It's not changing what we call the thermodynamics or the energy of the reaction. It's just going to make the reaction go faster. Okay, so let me go back. This is the graph you're supposed to draw. So you may want to pause and draw this, okay, first, and then come back in and listen. Okay, so hopefully you drew this. All right, so here's on the bottom here we have kind of the course of the reaction. So this is sort of like time going that way. Free energy is on the y-axis, and then we use the letter G, and that represents the free energy. And so that's the amount kind of in the molecules. And so you can see here, remember we talked about the reactants, let's say you have A, and you're breaking that down into B and C. Our reactants would be A, and our products would be C and B and C. And so, A, whatever that molecule is, it has a certain amount of energy stored in the bonds, a certain amount of free energy, or G. So let's say in this graph here, let's say this is A, my reactants, and then my products down here are B and C. And so you can see the products at the end, if you imagine, there's numbers here, going up this axis, 10, 20, 30, whatever, 80. Okay, let's just say, I'm just doing random numbers. Let's say the reactants have 80 units of energy. And then the products that we're going to form have 10. So that's not being changed. This is going to be what we call a downhill reaction, but I don't want to get into chemistry. And then you see here what we call the delta G. Okay, and the term, this little symbol delta, we say it delta, means the change in. Okay, and So delta G is referring to meaning the change in energy between the reactants and the products. And so the delta G does not change with the enzyme. In other words, a reaction has a delta G, basically this is the difference between the reactants and the products, okay? So that's not going to change. The enzyme's not changing that. But you can see the difference between the red line and the blue line. And you can see here, this is your activation energy right here, EA, okay? So if my reactants are here, before they will react, there's a certain amount of energy that's required to be put into them to kind of get them oriented and so that they will react. And we call this hill is the activation energy. So we have to put some energy in to get it going. Once we put that activation energy in, then it'll react and you'll get products. Okay? And so what you see here, and what you need to make sure you label, is this blue curve. The only difference between the blue and the red is the blue is without enzyme, what the activation energy would be, and the red is with enzyme. Okay? And so you'll notice whatever the energy that the reactants have and the energy the products have, and the delta G, the change in energy that's going to happen in that reaction, that's the same for both curves. That enzyme doesn't change that. All it changes is this hill. Think of it like, you have to, if you're on your bike, you have to get up a hill. You put some energy in to pedal up a hill to get to the top, and then you can just roll down the hill. Okay, think of this is the actual reaction. And going up the hill is the activation energy. And so all the enzyme does is lower. This is what the enzyme is doing, is lowering that activation energy. So you have to go up a smaller hill before you can go down the hill. Okay? And because we lowered the enzyme lowers this, it means the reaction can happen much faster and much easier. Okay? So that's a graph that's really important. It comes up a lot, and it makes sure you understand the reactants have the same, the products have the same energy, the delta G change in energy is the same, but the activation energy is just lower. Pick the graph with the lower hill as the one that's showing with the enzyme. Okay. Okay. So I'm just going to leave this here. Again, you can pause to fill in the blanks if it's hard to listen and go at the same time. But there are certain things that are going to affect how the enzyme works, just like in proteins. We already talked about how temperature and acids and bases will denature proteins and make them unfold and fall apart. Remember, enzymes are proteins, okay? So, this is really kind of the same thing we learned in the protein section, but we're talking about an enzyme that's a protein now. All right, so enzymes remember I said the word specific is going to be what we use a lot. Enzymes have a specific shape. They have a specific active site that binds a specific reaction. But they also have a very specific temperature, and we're going to see they have a specific pH also that they have to be at to work best, okay? So low temperatures, extremely low temperatures, cause reactions to slow down. That's true of any reaction. So remember we talked about when we were talking about water having a high heat capacity, remember when you have a low temperature, the kinetic energy of the molecules is slow. They're not moving around as much. As you heat up something, the molecules start moving faster, okay? And we call that kinetic energy is the molecular movement, okay? So as you heat something up, the molecules move more when we say they have more kinetic energy, okay? And so as the temperature increases, okay, and this is regardless of an enzyme, just any reaction, as a temperature increases, the reaction rate will speed up just because there's more molecular movement, more kinetic energy. The substrates, if you have a bunch of molecules and they're bouncing around, okay, they're going to collide with each other and maybe react into products, okay, more than they would if they're not moving around, right? So that has nothing to do with an enzyme. Just in general, if you heat up anything, the molecules move more, they collide more, and if there are things that are going to react in a reaction, the reaction will happen at a faster rate at higher temperatures, even without an enzyme. Okay. In this case, if you have an enzyme in there, so let's say I have, substrates in there, but then I also have my enzyme, which I'll draw as Pac-Man. Let's say the dots are the substrates that are going to go in there. If I heat this up, okay, the kinetic energy of all the molecules, the substrates and the enzymes, they start bouncing around, and the substrates might collide into the active site of the enzyme more. And so that you're going to get a faster reaction rate because not just because everything's moving faster, and some of the substrates might collide in a way that they might react on their own, but they're going to collide with enzyme. So the enzyme's going to make them react, okay? So temperature is going to increase the reaction rate of anything, whether there's an enzyme there or not. But at extremely high temperatures, okay, heat is also energy, and that can start breaking some of the weak bonds that are holding, remember the enzyme we said is like a pack. Here's my enzyme, and it's a amino acid chain. It's got weak bonds in there. It's a protein, and there are some weak bonds in here, okay, that are holding that shape together. And heat is going to can break some of these weak bonds, and so this shape could fall apart and end up looking like that in heat. Okay, if you change the shape of the enzyme, the active site probably changes too, and then the substrates don't fit, and then the reaction basically stops. And remember, we call that denaturation, when a protein loses its shape, falls apart, and since enzymes are proteins, it kind of applies here. Okay, so this is just a picture of this would be, by the way, this picture. If this is an enzyme, let's say this is an enzyme. Remember, it's a protein with quaternary. This would be a protein that has quaternary shape, quaternary structure, because you see 3 amino acid chains in the shape. Okay. Remember, if there's more than one, it's a quaternary. Most enzymes, remember, have tertiary or quaternary structure. So they either have one amino acid chain folded up in a blob, or they have more than one. And this is just showing you a picture. So it loses its 3D shape when it denatures. Okay, this is sometimes permanent and sometimes temporary. So if I heat up an enzyme, some of the weak bonds break and it denatures or falls apart. Sometimes if you cool it back down, it'll reform back to the normal shape and be fine. But most of the time, once it's denatured, it's done. Okay, this is showing you what I just said, but in a graph. Okay, so again, you might want to pause for a second, fill it in, and then listen. And so what you're seeing here is, temperature on the x-axis. As temperature increases, and this is measuring enzyme activity. Okay, or we could also call it the reaction rate. With the enzyme. Okay, and so you see that as temperature goes up, the reaction goes up too, okay, which I just said, that's due to increased molecular movement. And, so this is because there's increase in molecular movement. So there's more collisions between the enzyme and its substrate, or substrates, depending on what the reaction is. Okay, so the enzyme is, the important thing that you want to put over here, the enzyme is not denaturing here on this cold side of the graph. That's what people get wrong, okay? Cold temperatures don't make the enzyme denature, they just make the reaction go slower because molecular movement is slowing down. So we can see all enzymes are going to have like an optimum temperature at which they work best. That would be the top of the peak. So if I give you a graph and I say what's the best temperature for this enzyme, you just go to the peak and read down. And so for this one, it's around 40 degrees Celsius. But then once you get above that, okay, here's where the enzyme starts denaturing. Okay, so now we have the temperature is causing weak bonds to break. in the enzyme, and that's causing it to denature or fall apart. And so that's the enzyme activity over here decreases because the enzyme falls apart. It decreases over here just because molecules are moving slowly. Okay. And you'll notice here, by the way, human body temperature is 37 degrees Celsius, which is, so a lot of enzymes graphs we're going to look at are going to be peak right around this same temperature, 37, 38, 39, 40. Remember, we're 37 degrees Celsius, which is 98.6 degrees Fahrenheit, but a lot of graphs are in Celsius. Okay, so the optimal temperature for all enzymes, you can tell by looking at the peak, okay? But notice the point of this is that it's not the same. You know, it just depends on where the enzyme is. Like human enzymes are going to tend to all kind of have, like right here, like I just said, here's 37 degrees Celsius. It's humans. So notice the optimal temperature for most human enzymes peaks, you know, at that temp. Makes sense. That's where that enzyme kind of has evolved to live, so to speak, or function. So that makes sense. Whereas thermophilic bacteria, these are bacteria that live in, like hot springs or hot vents in the bottom of the ocean where it gets really, really hot. And they've evolved to live there. So it makes sense that the optimum temperature for the enzymes in that bacteria are higher, okay? Again, so you can pause and fill this in. It asks you what's the optimal temperature and why for each one. It depends on where that enzyme exists in nature, usually, okay? All right, the other thing that can affect an enzyme is pH. And remember, pH scale, just a 7 is neutral, like we said, water, which means it's not an acid or a base. Anything that's a base, as you go up, has a pH above 7, and anything below 7 is an acid. And as you go down, it's stronger and stronger. So this would, you know, pH of 1 would be a very strong acid. pH of 6 would be a weak acid, okay? And so enzymes are also pH that the enzyme is in can affect its shape and therefore its function as well. So enzymes are pH specific, meaning they work best at, there's a certain pH that enzyme, again, sort of lives in or has evolved in, that the shape will be correct. And if you change the pH, that changes some of the bonds and the shape of that enzyme, and that usually means it doesn't work, okay? And so this picture, you'll notice, looks very similar to the temperature one, where there's kind of a peak, and you can see the optimal pH. Just go to the top. This enzyme, whatever it is, works best at a pH of 8. And if you go below a pH of 8, the enzyme starts not, the activity or the reaction rate slows down. And if you go above. So what's important is that you realize that it's denaturing. On this graph, it's denaturing on both sides, okay? If you raise the pH or lower the pH from the optimal for that enzyme, it falls apart. Whereas on the temperature graph, okay, let me draw the temperature, you know, if we're doing temperature and against reaction rate, it only denatured on the hot side. And also, if you notice, the temperature graph looks a little more like gradual hill, and then, oh shoot, I don't want that straight line. It looks a little more like a gradual hill and then a crash. Whereas this is a little more of an equal hill, okay? And remember, on the temperature graph, it's only denaturing on that side of the hill. Okay, so it tells you to label the graph. You can pause and do that. I already kind of did that. It's denaturing on both sides, and that's its optimal pH, where it's going to function the best. Again, the optimal pH for all enzymes is not the same. It depends on where that enzyme functions. So here's an enzyme. Pepsin is an enzyme in your stomach, and our stomach has a pH of 2. You all probably know there's acid in your stomach. There's hydrochloric acid. So it makes sense that the enzyme that has sort of evolved to live in our stomach, again, they're not alive. I say live in quotes. But the enzyme in our stomach has an optimal pH of 2 because that's the pH in the stomach. Whereas in our small intestine is slightly basic. It has a pH of 8. It makes sense that enzymes in the small intestine work best at a pH of 8. if pepsin in my stomach ends up going to my small intestine, where it's the pH is 8, it's not going to work at all. Notice the activity on if pepsin goes above a pH of 4, it doesn't function at all. Okay. Okay. The next graph that you're going to look at, the other thing that can affect the reaction rate is the substrate concentration. And this is sort of silly. Like, it's kind of, I always say sort of like, duh. Like, obviously, if you add more substrate to the reaction, you're going to get a higher reaction rate because that's what's reacting. But notice that what you see here is substrate concentration. And sometimes we write that it like this. When you put something in brackets, it means concentration. So if you see an S with a bracket, that's referring to substrate concentration, how much substrate you have. And this makes sense, I think. Obviously, if we had like a test tube and we had enzyme and substrate in there, they're going to start reacting. If I add more and more and more substrate, okay, obviously I'm going to get more and more. Their enzyme, remember, can be reused. It's grabbing the substrate and spitting out product. But if I add more substrate, I get more product. That makes sense. But notice here it then levels off. This is what we call the V max, okay? V stands for velocity, max is the maximum. And this is the point of saturation, or Vmax, which just means this is as fast as this reaction will go, and then it's going to level off. So if I ask you to label the Vmax on a graph like this, where we're graphing substrate concentration versus an enzyme catalyzed reaction, just where the hill kind of levels off, that's the Vmax, that's the maximum rate of reaction. And this is kind of an important point here. We're assuming that the concentration of the enzyme is constant in this tube or this system. So usually when I'm in the classroom here, I like to say, like, okay, pretend like you guys are all an enzyme, okay? So let's say there's 20 of you, you're enzymes, and you're in a test tube. And there's no substrate right now, so you're just sitting there. And let's say I add a little bit of substrate, okay? So a few of you as enzymes are reacting, kind of bumping into your substrate, and you're grabbing them and making them react and spitting out product. But a lot of you are still just sitting there. You're not encountering a collision with the substrate because there isn't that much. So maybe 2 of the 20 are busy, and then if I add more and more substrate, now there's maybe 3, 4, 5, 6, 7, 8, 9, 10 of you enzymes are actually colliding with substrate and making product. And as I add more substrate, okay, so you can see that, like, when we get to the point here, I've added enough substrate. All 20 of you, if you guys are all enzyme molecules, there's so much substrate now that you guys are all grabbing substrate, spitting out products, grabbing substrate, spitting out product as fast as you can. You can't go any faster because there's a fixed amount of you. Each enzyme is going as fast as they can. And so that's where we would reach the Vmax, or saturation. Okay, again, you can pause if you need to read the notes and fill it in. Okay, and then we talked about how enzymes are specific. Each enzyme runs a specific reaction. This is just an actual example, and I think I even mentioned this. Lactase is the enzyme that breaks down lactose, which is, remember, a disaccharide, and it's made of glucose and galactose, the monosaccharides. Here is the picture of it. Okay, so here's lactose, a disaccharide. If you drink milk, you're drinking this. And then you have lactase, the enzyme, in your digestive system to break it down. And then you can absorb glucose and galactose into your blood, etc. If you're lactose intolerant, you don't have lactase. Okay, so you can't break down lactose. You can't digest it. And so you can see here's just a picture of what it would look like with shapes, because we're going to have you draw some stuff here as shapes in a minute. But so you can see lactase has a shape with an active site that fits lactose, and lactose binds in there. So this would be my enzyme plus my substrate plus, and that gives me my enzyme substrate complex that just shows them together. And then this would be my enzyme plus product. So you can see my enzyme is still there, same shape, but it's spitting out the products. It broke lactose down into glucose and galactose. Okay, and so if you don't have that enzyme, you can't do that. And the reason it causes a lot of discomfort is like cramping and gas and diarrhea. It's because there's E. coli in your intestines, and we'll talk about this later. But good E. coli, like remember the normal healthy bacteria we talked about. And so if you're not digesting it, they are. And the bacteria, when they digest lactose, produce a lot of gas and stuff. Okay. All right, so next you guys are going to do the enzyme activity. And so basically, there's a part where it's asking you to draw with shapes a reaction. And this is pretty much kind of what we're asking you to kind of come up with to use shapes, okay? And so here's, an example of some shapes. So you may want to take a screenshot of this just so you have this as to look back to when you start the activity. And you don't have to use these shapes. You can make up your own shapes. You can have your enzyme be Pac-Man and your substrate be this, or you can create your own shapes. Do them like that, or, we've given several examples. But this just gives you an example to draw. And so, you can see we have products, a couple substrates. And so on the enzyme activity, it's going to ask you to draw a catabolic reaction and an anabolic reaction. And so I'm just going to switch over and show you what I mean. So here's the enzyme activity. You're going to define some stuff. But here it's asking you to draw, in notability, a hydrolysis reaction, okay? Remember, a hydrolysis reaction is going to be one that's breaking things down. So you're going to have one substrate that gets broken down by your enzyme into like two products, okay? And so you're going to draw, like this equation, you're going to draw the enzyme, a picture of it, and the shape of the substrate, and then show them together like an arrow, and then show the enzyme, which is the same shape, and show two products, two shapes. So take whatever shape you use for A, split it in half and show products, okay? And then you're going to do the same thing, create an enzyme shape and substrate shapes that fit for a condensation. But remember, a condensation reaction is putting molecules together. So you're going to have two substrates, shapes that have to fit in your enzyme. Okay, so you're going to have an enzyme shape, and then you're going to draw two shapes for substrate 1 and substrate 2, show how they fit in the active site, and then show how they go together. You're just drawing shapes, okay? And then you're going to do a graph here. I think you guys remember how to do a graph. Remember, the independent variable goes on the x-axis. Okay, what you're altering, that's going to be temperature. And then your reaction rate's going to go here. Don't forget to write the units. I'll let you remember, uncertainty is plus or minus the smallest increment. So let's assume that the uncertainty for temperature, since it's not showing any decimals, let's assume it's plus or minus 1 degree Celsius. And again, the reaction rate will just be plus or minus 1 mole per minute, because we don't know the measuring device, but since the data is kind of written that way, we're going to assume that that's our smallest increment for uncertainty. Don't forget, your title has to have 3 things. Your subject, in this case our subject is the enzyme, okay? Although it doesn't give you, yes it does, the enzyme's name is catalase, okay? And the independent variable and the dependent variable. So come up with a title telling me what this graph is, okay? Using those 3 things. The enzyme name, that's your subject, and your independent and the dependent variable, okay? And do your best to finish that by the end. Since I'm not around to help, I will, I'll be a little lenient if you need more time and you're not finished by the end. Again, just you can message me or shoot me an email and finish it like after school. But I'd like you to try to finish by the end unless I hear from you. Okay?